So, hello and welcome to week 10 of the Algebra 1 course offered by NPTEL. I am Shubhajit Das, one of the TAs for this course, and hopefully you are attending Harish's sessions. So, as we keep doing every week, we solve problems from previous year assignment. So, let us start. Okay. So this week you have studied further on modules. You have probably seen the primary decomposition theorem and various other notions concerned with modules like free modules and yeah. So let us start solving the problems one by one. So let us look at the first problem. Okay. So most of the problems for this week are basically true and false questions. Okay. So let us start. So let us read out the first problem. So we need to determine what is the truth value of this statement, whether this statement is true or false, that there are only countably many irreducible Z modules. Okay. So we quickly recall the definition of an irreducible module. So a module M is said to be irreducible if it is non-zero and its only submodules are the zero module and the module M itself. It has no other submodules other than these two. So an irreducible module is the same thing as a simple module, right? Only submodules are the trivial module and the improper submodule, that is the whole module. So we need to prove that, we need to rather determine whether this statement is true or false, that the only countable, that the only that there are only countably many irreducible Z modules. Okay. So yeah, so this is this is very easy. So first of all, so we can do this using let's say we can use the we can use the primary we can use a structure theorem for modules over a PID. In particular, we can use a structure theorem for finitely generated modules over finitely generated abelian groups, which are just Z modules, right? So suppose, so we just claim this. Okay, this is our claim that every irreducible Z module is of the form Z mod P, where P is a prime integer, prime in Z. Okay. So first of all, before we move on further, so let M be an irreducible Z module. Okay. Then these are our observations, which are very easily checked. Okay, you can check this very easily. So observation, the first observation is that M is finitely generated. So so why? Because assume it where M is not finitely generated, then we can take any non-zero element in M, right? And we can take the submodule generated by that. That will neither be trivial nor be the whole M, right? Whole of M, which would contradict the fact that M is irreducible. So M must be finitely generated. And secondly, what we have is a direct implication from this, that since M is finitely generated as a Z module, so we know that M is isomorphic to Z, some direct sum of copies of Z, right? Direct sum of copies of Z, let's say finitely many copies. How should I write? So yeah, it's a finite fold direct sum. Direct sum, some torsion part, right? So Z mod P1 to the power alpha 1, direct sum Z mod P2 to the power alpha 2, direct sum dot 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 direct sum z mod p r to the power alpha r where p1, p2, pr are not necessarily distinct primes, not necessarily distinct primes, and alpha I is greater than equal to 0 for all I from 1 to r, right? So yeah, in fact we can take greater than equal to 1, right? Alpha is greater than equal to 1 for all I running from 1 to r, right? Oops, I didn't leave any further spaces here. Let's see. Right. Now, since z is irreducible, observe that if there are two summands of m in this decomposition, if you have at least two summands of m, then you can get at least two non-trivial submodules, right? So for example, m is of the form a direct sum b, then a direct sum 0 is a submodule and 0 direct sum b is a submodule. Both are non-trivial and both are proper, right? So that means that it must have exactly one summand in this, right? So from this we can further imply that since capital M is irreducible, hence capital M must be isomorphic to, that is, it must be of the form z mod p1 to the power, let's say p to the power alpha, let's say p to the power alpha, or some prime p and alpha greater than equal to 1, right? Now I didn't say that z could also be of the form z, I mean m could be equal to z, right? But if it were of the form z or some direct sum of copies of z, you would have the same problem, right? That is, it would contradict the irreducibility, because we know that z in particular has many proper non-trivial subgroups, right? So that means it must be of this form z mod p to the power alpha. But then again, if it is of the form z mod p to the power alpha, we claim that alpha has to be equal to 1. So this implies that alpha is equal to 1 as m is irreducible. The same thing is, same logic or same reason is being applied again and again. If alpha is greater than 1, then z mod p to the power alpha indeed will have more non-trivial proper submodules, right? For example, say alpha is something strictly greater than 1, then you could just take the element p to the, you could just take the class of p, right? This would be non-zero, you take the submodule generated by this will be non-trivial, and this will still be proper, right? Because it will have p to the power alpha minus 1 elements in it, right? That is, the order of this element in this abelian group is precisely p to the power alpha minus 1. So it would definitely be proper and non-trivial as well. So that means alpha is equal to 1, so that thus m is basically isomorphic to z mod p, ideal generated by p, where p is, what is p, where p is a prime, right? And that basically says that every irreducible z module is of the form z mod ideal generated by p, where p is a prime basically, right? And that's it, it's as simple as that. So anyways, now the point is that we know that there are countably many primes, right? So there are countably many primes, hence there are countably many irreducible z modules, right? And that's it. So answer is therefore that the statement is true. So we have that the statement is true. It will be a true statement. That is, there are only countably many irreducible Z modules. Now in order to solve this problem, I have basically used the primary decomposition theorem here. But then again, let me remind you, it's not a necessity. I use the structure theorem for modules over a PID, finitely generated modules over a PID, but there is no necessity that you have to use that. Okay, it could be done in a much more elementary way. Okay, you could just assume you could just take an irreducible Z module and then just show that it has to be of the form Z mod ideal generated by P. It's very simple. You don't need to invoke this machinery here, but I just wanted to display one of its uses. That is why I use this theorem. You could alternatively give a more elementary proof. This is very easy. Okay, so let us move on to the next problem. Okay, so this is question 2. So let us move on to the next. Yeah, so this is problem 2. So we are given that let R be a commutative ring and let F be a free module of finite rank. Okay, so we know what a free module is, right? A free module is just a module that admits a basis, right? It is a module that has a basis, right? So that is, in other words, it has a set of elements in it which freely generates the module, which is linearly independent over the base ring and which spans the entire module. Okay, so let F be a free module of finite rank. Alternatively, you could also define a free module to be a direct sum of copies of the base ring, right? That is, a free module F is a free R module F is an R module which is isomorphic to a direct sum of copies of R as an R module, right? So now assume F is a free module of finite rank, which means that it has a finite basis. That is, there is a basis of this module, say E1 up to En, okay, consisting of finitely many elements of F. Okay, now to determine this, whether that this is true or false, that any other basis of F will have exactly n elements. So let's see. Okay, so I just want to point out the fact that this is not true in general. Okay, if you are given a ring and if you are given a free module over that ring, that is a module which is a direct sum of copies of that ring, it's not necessary that every basis will have the same number of elements in it. Okay, I mean, more specifically, you can say that if the module has a finite basis, then it's not necessary that every basis of the module will have a finite will have the same number of elements, okay, as the given basis. Okay, but here the most important thing is the fact that we are taking a commutative ring. If the ring is commutative, then this statement is indeed true, that if F is a free R module where R is a commutative ring, and if you take any let's say you take a basis of the module which has n elements, then any basis will have exactly n elements. So this statement is indeed true, and the important thing is that we are considering a commutative ring here. Okay, so this is very, very important. So let's see. Now let me just give you first of all a rough sketch of the idea involved in proving this. Okay, so you take this free module, you know that it's a direct sum of copies of the base ring, right? Now it's just a module, right? It's a module over the commutative ring R. Okay, what we want to do is we want to sort of extend our scalars. Okay, so right now our scalars are restricted inside a ring, right? So what we want is we want to obtain a field out of that ring. Okay, and we want to obtain a module over that field, that is, we want to obtain a vector space over that field. Okay, and since the original module over the original commutative ring has n elements, we want to show that this vector space we want to show that the original basis gets translated or rather transformed into a basis for the vector space over the base field which has exactly n elements. Okay, so we started with a basis of n elements for our module and we obtained a basis of n elements for our vector space, right? Now there is something important, there is something very rather I would say very popular about vector spaces, that any two bases of a vector space have the same number of elements. So initially if we started with two bases for the module, that is one has n elements and the other has m elements, then we come to this vector space and we obtain a basis with n elements and we obtain a basis with m elements in the vector space. But since it's a vector space over the field, that means that n has to be equal to m, right? And then we are done. So this is the rough idea, and there is a very sophisticated way, or rather machinery, for writing all this, okay, which is usually done in terms of something called tensor products and extension of scalars, okay. But we don't want to use all that machinery here. In fact, we will be doing essentially the same thing, but we will be doing it from a much more elementary, I would say using much more elementary tools that you already know, okay. So first of all, since R is a commutative ring with 1, okay, it has a maximal ideal M, that we know, right? And the way we prove this is by Zorn's lemma, which says that if X is a partially ordered set such that every chain in X, that is every totally ordered subset of X, has an upper bound, then X contains a maximal element in it, okay. So since R is a commutative ring with 1, it definitely has a maximal ideal L and M, and once we have a maximal ideal, we can produce a field, okay. So consider the field K, consider the field K is equal to R mod M, okay. This is a field, right? We call it K. So what, as I said, what I want to do is we started with, so let's we started with a free module F, right, free R module. So what we want to do is we want to obtain from this module a vector space over K, right. So consider this vector space. So indeed F is a module over R, but it's not necessary that F will also be a module over K, that is R mod M. It's not necessary at all. In fact, this will be true if and only if the ideal M is contained in the annihilator, that is since M is a maximal ideal, this will be true if and only if M is exactly equal to the annihilator of the module, but this might not be true in general, right. So it's not necessary that F will be a free module, F will be a vector space over K, right. That is, it's not necessary we can put a vector space structure on F, K vector space structure on F, okay. So as I said that something M, suppose M is an R module, then, and suppose alpha is an ideal of R, then M is an R mod alpha module if and only if alpha is contained in the annihilator of M, right. So what we want to do is we want to modify our module F here in a certain way, so that we get a new module whose annihilator is actually contained in such that M is actually contained in the annihilator of that, okay. So what we do for this is consider the module, consider the R module. So what is our R module? It's precisely F mod MF, okay. So recall what is MF? MF is just I don't know why it's not yet on the screen. The screen has got stuck, I guess. Anyways, I guess it will come, just wait for a minute. Yeah, so consider the R module F mod MF. What is MF? MF is precisely the submodule of F consisting of all elements which are finite sums AI, that is summation AI BI, where AI is in M and BI is in the module F, okay. This is an R submodule of F. F is itself an R module, so we can take this quotient F mod MF, and this is an R module. But now observe that every element of M actually annihilates this R module F mod MF, right. That is, M is contained in the annihilator of F, annihilator of F mod MF, okay. So check, so this is what I leave for you to check. Check that this scalar multiplication which maps K cross K cross F mod MF into F mod MF, okay. What does it do? It maps an element M plus R, which is an element of the field K, the quotient. So it maps an element M plus R comma MF plus A onto MF plus RA, check that this is a well defined scalar multiplication, that is external composition or a well defined action of K on F mod MF. Okay, scalar multiplication or well defined, let's say action, it would be better to use that word, well defined K action on F mod MF, which makes F mod MF into a K vector space. So you can check that very easily. Okay, now we have obtained a K vector space. Okay, so it's time to consider what it does to the basis. So let us see what this basically does to the basis. So this is what I again leave for you to check that so you have a map from F to F mod MF. So check that MF plus E1 comma MF plus E2 plus comma MF plus En, right, where E1 up to En is the original basis that we took for the free module F over R. So check that this is a basis of the vector space of the K vector space F mod MF. That is, check that this particular set is linearly independent over K as well as that it spans F mod MF. It clearly spans F mod MF since E1 up to En span F. Okay, and you can check that this is linearly independent, right? That also is very easy to see, right? Precisely what you would have is, if you take MF, if you just take a linear combination of these vectors over K, so that linear combination, if you just split, if you just club things together and write things properly, you just arrive at MF plus R1E1 plus R2E2 plus dot plus RNEN, right? And you assume this is 0, which would mean that R1E1 plus R2E2 plus dot plus RNEN is in MF. Okay, and from that you can easily conclude, based on the fact that E1 up to En are linearly independent over R, you can conclude that R1, R2, all those coefficients have to belong to M. Okay, that is what I mean by this is that the scalars have to be 0. Okay, so this is a basis of the K vector space. Okay, so which means thus now we are almost done. The argument is over. So what we did was, we took an arbitrary basis, and out of that we obtained a basis for our vector space F mod MF consisting of the same number of elements, right? So thus, if let's say, how should I write this? X and Y are bases for F over R, for the free module F over R, such that cardinality of X is N and cardinality of Y is M, right? Then MF plus X. Okay, so what I mean by this is this, that is, then MF plus little x, such that little x is in capital X, this set, and MF plus little y, such that little y is in capital Y, this set, right, are bases for the vector space, for the K vector space F mod MF. Okay, which implies that N, which is the cardinality of this set MF plus little x, such that little x is in capital X, right, is equal to the cardinality of MF plus little y, such that little y is in capital Y, right, which is equal to n, right? And that basically finishes the proof. Okay, so m is equal to n. Okay, hence any two bases of f, any two bases for f over R have the same number of elements. Okay, and that is what this problem is all about. So the statement is therefore true. So the answer or the verdict is true, right? This is a true statement, and that finishes this particular problem. Okay, so this is what is very important about commutativity here. Okay, we need commutativity for this, and if the ring were not commutative, then this would not hold, as is suggested by our next problem. But before that, let me just add to this something important here. Okay, so a definition that might be very useful for people who are studying, who are interested in studying non-commutative ring theory. Okay, so which is precisely the definition of an IBN ring. So let me just add this here. So let me just add this here. So we can make this small definition. A ring R is called an IBN ring, that is invariant, or rather I should say is said to have. So a ring R is said to have IBN invariant basis number property if and only, or rather this is a definition, if for all natural numbers m comma n, okay, r power m is isomorphic to r power n, implies that m is equal to n. So what I mean by this is r power m is just a free module of rank m. I mean it's a free module that has a basis of m elements, and r power n is a free module that has a basis with n elements. Okay, so these two will be isomorphic if and only if m is equal to n. Okay, that is, if we take any two finitely generated free modules over, if we take any finitely generated free module over R, then any two bases of that module will have exactly the same number of elements. Okay, this is what IBN property, invariant basis number property, says, and what we just proved is that commutative rings have IBN property. So as an example, commutative rings have IBN. Okay, proved above. This is what the above exercise was all about. So proved above. Right. So this is the infamous invariant basis number property. Okay. Sorry. Yeah. So let's move on to the next problem. Okay. Okay, so this is question 3. So let R be a ring which is not necessarily commutative, and let F be a free R module of finite rank. The same situation as problem 2, but now R is any ring, not necessarily commutative. Then we have to show whether this is true or false, that any other basis of F will also have exactly n elements in it. And we claim that this is not true. Okay, so this is false. So we need to construct a counter example for this. So this is the most famous counter example. Okay, so let me just write it down. So consider what should I say? Let's say consider V is equal to direct sum over natural numbers R. That is, we are taking direct sum of R n-fold copies of R, right? That is, you are taking a direct sum of n-fold, that is natural countably infinitely many copies of R. So this is an R vector space. So V is an R vector space. There is no doubt about that. Okay, and so what we do is we consider our ring R. Let R, this R is different from R what we have written above. Okay, so let R is equal to the endomorphism ring of V. Okay, which means that this is precisely all R linear maps, set of all R linear maps from V into V. Okay, endomorphisms are precisely, as you know, they are precisely morphisms, or they are precisely morphisms whose source is equal to their target, right? Whose domain is equal to their codomain, whose domain is equal to the codomain, or whose source is equal to the target, right? Self maps. So and they have to be R linear. Okay, so we are taking R linear mappings of V into V, and we are calling this ring to be R. Okay, so then you can check this, that R is R as an R module. We know every ring is a module over itself, right? And in particular it's a free module over itself, right? And you can check this, that R will be isomorphic to R square. Okay, so this is very easy. Indeed, the idea for checking this is this, that R square, what is R square? R square is R direct sum R, right? So you can check that R square, which is R direct sum R, is just hom, that is all R linear maps from what to what, from V to V direct sum V, right? Yeah, all R linear maps from V to V direct sum C, V to V direct sum V, right? Indeed, why am I saying this is precisely because V comma V direct sum V, that is all R linear maps from V to V direct sum V, is precisely equal to all maps from V to V. I mean, you can just, what I am trying to say here is this, that this is isomorphic to hom R V comma V cross hom R V comma V, right? This is what it is. Okay, so yeah, let me just write it more in a much nicer way. So R square, which is R cross R or R direct sum R, doesn't matter because we are taking the product or the co-product, that is a direct sum over a finite set. So this is hom V comma V, that is end V, right? All endomorphisms of the object V in the category of vector spaces. So eta cross hom R V comma V, that is you are looking again at all endomorphisms from V to V, which is your R, ring R, right? So this is precisely hom R V comma V direct sum V, right? Or you could also say this is hom R V direct sum V comma V. It would be the same thing, right? So yeah, I think it would be better to write it that. I mean, it's the same thing, doesn't matter, but V direct sum V comma V, right? Anyways, why? Yeah, I didn't explain this. So why am I saying that this and this are the same? So indeed, observe that if you want a map from V direct sum V to V, that is basically the same thing as giving a map from V to V and a map from V to V, right? Exactly. So every pair of maps from V to V, you take F to be a map from V to V, and if you take G to be a morphism from V to V, then that will give you a morphism from V direct sum V to V, right? Just precisely you will be adding, right? Addition. And conversely, if you are taking a map from V direct sum to V, then you have a map from V to V and a map from V to V, which is precisely obtained by taking, which are precisely your, what should I say, which are precisely your projections, right? Yeah, right. So that means that hom r v direction v comma v is the same as hom r v comma v cross hom r v comma v. But then again, what is hom r v direction v? That is, what are all the morphisms from v direction v to v? So v direction v is direction in r direction in r comma v. I am not writing this v, and since you are taking direct sum of two countable many copies of r, you get the same thing, right? I mean, what I mean to say is you are taking a direct sum of two copies of two objects, or rather direct sum of two modules, okay, each of them being a direct sum of countable many copies of r. So you just get the same thing, hom r direct sum in r comma v, right? That is v comma v, which is just r, and which therefore says that r square is r, isomorphic to r, right? Thus r has a basis with one element and a basis with two elements, okay. Indeed, what we did can be done for any n, not just two. You can just show that r is isomorphic to r n, where n is some natural number. The same trick will hold. Instead of taking a direct sum of two copies of v, you would be taking a direct sum of n copies of v, and you would apply the same argument, okay, and what you have is this, okay. So that means that this r, this ring r that we have constructed, which is precisely the ring of all ring of all endomorphisms of the object v, right, ring of all endomorphisms of the object v, this particular ring that we have taken here is does not have the invariant basis number property. Yeah, so let's move on to the next problem. Okay, so we again need to determine whether this particular statement is true or false, that let mn be equal to z mod nz, which is considered as a z module for all any natural number. That is, you fixed a natural number n and you define this z module mn to be z mod nz, okay. So then we need to determine whether this is true or false, that the direct product of the mn's is isomorphic to the direct sum of the mn's, okay. So before I move on, let me just recall what are the definitions of direct product and direct sum. By direct product I mean that you are taking all tuples, all sequences of elements of mn. So basically you take since we are indexing over natural numbers, an element of the direct product will basically be a sequence xn, let's say, where xn belongs to mn. And what about the direct sum? The direct sum of all these mn's will be a submodule of the direct product, where you will be taking sequences where xn belongs to mn and all that, nth component is in mn and all that, but with the further restriction, or with the added restriction, that every sequence will have only finitely many non-zero elements, okay. That is the entries in a sequence will vanish cofinitely, okay, will vanish on the complement of a finite set. So let's say 1 we can take here. So let's say 1 1 1 1 1, this is, and so on, this will not be an element of the direct sum. An element will precisely be a sequence in which there are only finitely many non-zero terms, okay, finitely many non-zero entries or finitely many non-zero components. And I mean, this is of course an internal description, but as you already know by now that I am more interested in universal properties of objects, right? That is, how do objects sort of connect to all objects, right? Yeah, so direct sum and direct product are basically, even though they might look the same, that is, the direct sum is a submodule of direct product, even though they might be looking as if they are somewhat similar, but there is a significant difference between the two. Indeed, the direct sum has been engineered in such a way so that you can define maps out of the direct sum, while the direct product pi is defined in such a way so that you can define maps into the product. Okay, so direct sum is characterized by arrows coming out of it, and direct product is characterized by arrows going into it. Okay, and this is what their respective universal properties are. Okay, so we can let's not digress too much in this. Okay, but yeah, even though they might look as if they are somewhat similar, they are completely different. Okay, both are different kinds of universal constructions, rather dual kinds of universal constructions, dual to each other. Anyways, so then product of Mn will be isomorphic to direct sum of Mn. We claim that this is false. So why is this false? So before we move on, let me just pause for let's say 1 minute, and if you want to think about this, you can think. Yeah, so let's quickly go through this. Why is this false? So they are false precisely because, observe, both are abelian groups, right? Both are Z modules, but one of them will be a torsion module, torsion Z module, while the other will not be so. Okay, by a torsion Z module, recall what I mean by a torsion Z module. A module over Z is torsion. It's called a torsion Z module if and only every element of the module is a torsion element, which means that if you take any element in the module, then there will exist a non-zero scalar, non-zero integer in this case, n, which annihilates that element, right? That is, n times that particular element will give you 0. This is what a torsion Z module is. And the direct sum, because of its construction or its internal description, it is a torsion module, while the product isn't. The product isn't 1. Okay. So claim is direct sum Mn, any natural numbers, is a torsion Z module, but product Mn, any natural numbers, isn't 1. So yeah, so let me write it more clearly, is not a torsion Z module. And the answer is very easy. Okay, it simply is because of the fact how direct sum Mn looks internally. Okay, so let Xn be an element of the direct sum Mn, n in natural numbers. Okay, then there are finitely many integers or indices, I would say, n1, n2 up to nr, such that in natural numbers, such that such that xi is equal to 0 for all I not equal to n1, n2 up to nr. That is, it will have any element of the direct sum, as I said, will have exactly finitely many non-zero elements, right? Non-zero entries, right? So this is true. So we know that x at n1, x n2, x dot dot x nr, all these elements might be non-zero. Other than all these elements, everything else is 0, right? So we can just focus on these elements. Okay, and these are actually elements where these are, so x n1 is in mn1, that is z mod n1z, right? X n2 is in z mod n2z, right? Precisely how what Mn was, right? Yeah. So dot 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 dot. So we arrive ultimately at x n r, which is in z mod n r z, right? Isn't it? So let little m be the LCM, least common multiple, of n1, n2 up to nr. Okay, then since n1 divides m, we know that m dot xn1 is 0, n2 divides m, so m dot xn2 has to be 0 because xn2 is in z mod n2z, xn1 is in z mod n1z, right? So then m times xn, the entire element xn that we took is 0, okay, in the direct sum mn. And the LCM, the integer little m, the LCM that we took is clearly greater than 0, okay, that's obviously true, okay. So since xn direct sum mn is an arbitrary element, hence every element of the direct sum is a torsion element, so that direct sum mn, n in natural numbers, is a torsion Z module, okay. But this is not true for the direct product, and the reason is very easy. So this is true, but the element 1, 1, 1, 1 and so on in the direct product, this is a valid legitimate element in the direct product, right? This element is not torsion, okay, in the direct product mn in natural numbers. And the reason is again very easy, right? You can just take any in non-zero integer m. We claim that m times this element will not be 0. Why? Because you can just take another integer which is relatively prime to m, right? So in that particular component, after multiplying by m, you will not get a 0, right? Yeah. So indeed the above statement was false, that is the direct sum and direct product are actually not isomorphic. Thus the direct product mn, n in natural numbers, is not isomorphic to the direct sum mn, n in natural numbers. They are not isomorphic, okay. So the above statement was false. So the answer is false. Okay, so let's move on to the next problem quickly. So again need to determine whether this is true or false, that any direct sum of free R modules is free. This is very obvious, it's true, right? Every free R module is a direct sum of copies of R, as I said, and if you take a direct sum of such direct sums, you will get a direct sum of copies of R, which means that it will be free. So let mi such that I is in some index set be a collection or a family of free R modules, then for every I in I there exists what should I say, there exists some index set ji, let's say there exists a set ji, right? There exists a set ji such that mi is isomorphic to, we can in fact write equal to, such that mi is isomorphic to such that mi is isomorphic to direct sum of copies, ji many copies of R, right? So how should I write this? Ji R, right? Maybe this is the correct notation. Okay. Thus what can we get? Thus direct sum mi, if you take direct sum of this family I in I, this is just direct sum I in I of direct sum ji R, which is isomorphic to or equal to direct sum what should I say, this is direct sum disjoint union ji I in I R, right? And this is clearly free, this is clearly free, right? And which means that the statement is true. So answer it's true. So this statement is again true, there is no doubt about it. Okay, so let's move on to our next problem, okay, which is question 6. Okay, so let R be a commutative ring and let F be a free R module of finite rank n, which means, as we said, that F is exactly isomorphic to a direct sum of n copies of R. F is R direct sum dot 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 direct sum R. Okay, and assume that M is any R module. So we need to identify which of the following statements are correct. Okay, so we need to identify which of these statements is correct. Okay, and what we do is we observe that the second part, B, is actually a special case of A. I mean, A is actually a special case of B, right? So in what sense we'll come to that, but let's just try to show that B is true first of all. Okay, so we know that F is isomorphic to, or we can say equal to, direct sum of n copies of R. So R direct sum dot 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 direct sum R, right? This has been taken n times. Okay, then we know that hom R F comma R direct sum dot 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 direct sum R, this is just isomorphic to hom R. I mean, yeah, before writing let me just say why. So what is hom R F comma R direct sum direct sum direct sum? This is precisely the set of all morphisms from F to R direct sum dot dot direct sum R, right? It is precisely the set of all morphisms, that is R linear maps or R module homomorphisms from F to this, right? All arrows in the category of R modules from the R module F to the R module R direct sum. Oh, sorry, yeah. I should be focusing on M, right? F comma M, right? So this is, yeah, so this is the same as hom R direct sum R comma M. So this is precisely the set of all arrows in the category of R modules from this n-fold direct sum of copies of R to M, right? So it is the set of all arrows or the set of all maps or the set of all morphisms from R direct sum dot dot direct sum R to M, right? All arrows from this to this. Now what is this? So as we have already said that direct sums are coproduct constructions. That is, what I mean by this is they are engineered in such a way that you can, they are characterized by maps coming out of them, right? So you can check this, as I have also already mentioned this, so that a map from R direct sum dot dot direct sum R to M is the same as a map from, as n maps from R to M. Okay. Let me repeat this statement. A map that is an R linear map or a morphism from R direct sum dot dot direct sum R to M from direct sum of n copies of R to M is the same as taking n maps from R direct sum n maps from R to M. Okay. So this is isomorphic to the product I running from 1 to n, product of n copies hom R comma M, right? Isn't it? So you take n maps from R to M, you take an element F1 from R to M, an arrow F1 from R to M, you take a morphism F2 from R to M, you take a morphism F3 from R to M, and so on, Fn from R to M, n morphisms you take, then this will allow you to cook up a map from R direct sum dot direct sum R to M. And conversely, if you take a map from R direct sum dot direct sum R to M, then you get a map from, you get n maps from R to M, right? Precisely what you do is you take R direct sum dot direct sum R to M, you take this map, and you already, let's say R is included in this at the first component. Okay, so this means that 1 goes to 1 0 0 0 and so on. So you compose these two maps to get a map from R to M. Again you include R in the second component, second summand of the direct sum. Okay, so so that x goes to 0 1 0 x 0 0 and so on, right? So you compose these two maps. Okay, you again get a map from R to M and so on. This is what I am trying to say. Okay. Right, yeah. So it's the same thing, right? So getting n maps from R to M is the same as getting a single map from R direct sum R dot R direct sum R to M. Okay. Now finally this last part is again easy. So observe what is Hom R comma M. That is, in other words, what is a set of all morphisms from R to M, or the set of all arrows from R to M, set of all R linear maps from R to M. Okay. So observe that every R linear map from R to M is fully determined by where it takes 1, right? The image of 1 gives you an element, the image of 1 completely determines the entire map, right? And you can map 1 freely to any element. Why? Because R is a free R module over itself, with basis given by the element 1. So 1 can be mapped freely anywhere we want, and then what we do is we use the universal property, right? We use the universal property of a free module, which says that as we have mentioned this previously, that a module M, suppose M is a free module over a set S, then the universal property is this, that given any set map from S to any module N, okay, then this map will factor uniquely through the inclusion from S into the free module, right? That is, there exists a unique map from the free module to the module N, such that this new map from the free module to the module M is an extension of the map from the generating set to M, generating set to N, right? Yeah. So every R linear map from R to M is basically the same as giving an element of M, and conversely every element of M gives you an R linear map from R to M. So what I am saying is, this is Hom R comma M is isomorphic to M, right? So this is product I running from 1 to M, and since we are taking a product over a finite, I mean we are indexing this product by a finite set, so this is the same as direct sum I from 1 to M, okay, which basically proves your second one. So let me just add a note here, okay. So note is this, that observe that Hom R comma M is isomorphic to M, okay, for every R module M. And this isomorphism is not an arbitrary isomorphism, that it doesn't depend on M, okay, it's a natural isomorphism. These isomorphisms are all natural, okay. So what I mean by this is these isomorphisms are natural in M, okay. So what I mean by this is that if you just change the module M to some module N, so you get Hom R comma M to M, you get a map, and you get a map Hom R comma N to N, right? So these two maps will actually not be arbitrary, but they are I mean these maps are defined in the same way. For the way you define the map, the first map for M, you define it in the same way for N, okay. There is again more precise language to frame all these things, that is, you take any map from M to N, any R module map from M to N, and you get a square, right? That, but I mean you get a diagram of modules and maps. That particular diagram should commute and all that, but that's all just fancy language to say the mere natural thing, that these maps, these isomorphisms that we are talking about from Hom R comma M to M, these isomorphisms are defined in the same way for every module M. It doesn't depend on making any arbitrary choices. These isomorphisms are defined uniformly in the same way for all modules M, okay. But the naturality or this uniformity is not important here. What is important here is the fact that Hom R comma M is actually isomorphic to M for every R module M, okay? And this is what we used in this above proof, okay. So B is correct. So B is therefore correct. And what about A? So A follows in the same way. I mean A follows easily. So Hom R if comma R, this is isomorphic to, as we know, as we have already as we have already done from B. So this is isomorphic to direct sum I running from 1 to N R, right? Just put R in place of M here, okay. M was an arbitrary R module, so this is just isomorphic to F, okay, as F is precisely R direct sum dot direct sum R, okay. So thus A is also correct. correct. So A and B are both correct, okay, and that finishes this particular problem. So let us move to the final problem. This is very easy, it will just take only 2 minutes. So let us read out the question first. So let M be a finite abelian group which is naturally considered as a Z module which has order 2 to 5, right. So let's just decompose 2 to 5. 2 to 5 is equal to 3 square times 5 square, if I am not very wrong, okay. Yeah, so then the order of the 3 prime, so we need to identify which of these statements is correct. The order of the 3 primary component is 3, 3 primary component is 9, 5 primary component is 5, 5 primary component is 25, okay. So what is a primary component? So basically recall that if you take, if G is a finite abelian group, okay, then G is isomorphic to a direct sum of cyclic groups, right, of prime power orders. This is a structure theorem for modules for finite abelian groups, and which is just a special case of the structure theorem for finitely generated modules over a PID. So G is isomorphic to Z mod P1 to the power alpha 1 direct sum direct sum Z mod PR to the power alpha R, right, where, as we have already said, where P1, P2 up to PR are not necessarily distinct primes, and alpha I is greater than or equal to 1 for all I running from 1 to R, right. So what is a, so the primes Pi might not be distinct from each other, okay. So if you just collect all the terms or all the summands together in which the prime Pi are the same, right. So basically, how should I say this? So let's say maybe this would be ideal, right. So if P1, P2 Pk, let's say, where k is less than or equal to R, are all equal to P, right, are the only primes equal to P, each equal to P, let's say, equal to P, that is, these are the only primes equal to the prime P, right, each equal to prime P, that is, every other prime is different from P, right, then the P primary component of G is Z mod P1 to the power alpha 1 direct sum direct sum Z mod Pk to the power alpha k. This is the P primary component of it. That is, what you do is you collect all primes Pi which are equal, okay. Let's call this common prime to be P, okay. Then this direct sum of Z mod P to the power alpha 1 direct sum Z mod P to the power whatever power there is direct sum Z mod P to the power whatever power there is, okay. You are collecting all the primes which are equal to P, okay. So that particular direct sum, which is just summand of G, that is called the P primary component of G. And what basically your structure theorem says is that every finite abelian group can be written as a direct sum of its primary components for different primes, okay. So that is, you have P primary component direct sum, Q primary component direct sum direct sum, whatever, how as many primes there are in the cardinality of G, right. Is each equal to P, then the P primary component of G is, yeah. So now we are in the right place to solve this problem. So That means what, so if you take the p primary component, the order of the p primary component will be exactly equal to the highest power of p dividing the order of g, right? So thus the order of the p primary component of G is the order is is we can say the order of Z mod p1 to the power alpha 1 direct sum dot 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 direct sum. So we can just write, I should also write Z mod p to the power alpha 1 direct sum Z mod p to the power alpha k, right? That is all these primes are equal to p. So this is the order of Z mod p to the alpha 1 dot 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 Z mod p to the power alpha k, right, which is p to the power alpha 1 plus dot 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 plus alpha k. That is, so this is the order of the p primary component of G, that is the highest power of p dividing G. P dividing the order of G. Now since 2 to 5 is 3 square times 5 square, so the order of 3 primary component has to be equal to 3 square, right? The highest power of 3 dividing 2 to 5 is 3 square, that is 9. So the order of the 3 primary component is 9. Whatever that primary component is, it can be Z3 cross Z3 or it can be Z9, right? Doesn't matter, but its order has to be 9, and the order of the 5 primary component will have to be 5 square, which is 25. Thus, which options are correct? So thus order of 3 primary component is 9, order of 5 primary component is 25. So thus B and D are correct. And that basically finishes this problem. So let me just tick mark it. B and D are correct. Okay. Okay. So that's it from my side. And if you do have any questions, please do email, and you already have my email ID. And the problems were very easy today, but nevertheless the solutions involved are some very valid and important ideas that are very recurrently used in module theory and in algebra or in category theory, or maybe let's say in mathematics in general. So please do have a look at all these things, and if you have any questions, do let me know, and please do attend Harish's sessions, which are held on Fridays. Okay. So that's it from my side, and so see you next week, which will be week 11, and let's solve some more problems. Okay. So bye.